Another text problem. We have a velocity function v equals 1 over 1 plus t, where v is understood to be in, I believe, meters per minute, the speed of a turtle, and t is the time in minutes. I believe that was the content of the problem. We'll see for sure. Or you can look that up, but it doesn't matter. In order to, we're asked to make an approximation of how far the turtle travels in 1 minute. So we're also asked to use an interval of 0.2, a delta s or a delta t of 0.2 in doing this. So we begin with t equals 0 and let t take values 0.2, 0.4, 0.6, 0.8, ending at the ending value of 1. And we calculate v for each of these t values simply by plugging each t value into the function. That's very simple and straightforward, and I believe we get these results. Now, in order to make the best possible, or not the best possible, but a fairly accurate approximation here of delta s, which is going to be our distance or displacement, we're going to first calculate average velocity in each interval. Average between 1 and 0.83 is 0.92, and between 0.83 and 0.71 is 0.77, and so forth. So we easily calculate average velocities on each of the 1, 2, 3, 4, 5 time intervals we have from the 6 t values. And then we simply multiply each average velocity by the time interval, which is 0.2 seconds, or 0.2 minutes in each case. Multiplying 0.92 meters per second by the 0.2 meters per minute by the 0.2 minutes, we get 0.18 meters. And then multiplying each of the average velocities by its 0.2 minute duration, we get the different delta s's. And note that we can add these up. This says delta s total equals 0.69. It might be written a little small. It might be a little bit hard to read what this says, but I think you can clearly see the 0.69. Now, the text problem actually asks you to find a lower and an upper estimate using the ideas of a lower and upper estimate. So we come over here and look at the situation. First, let's look at a graph. Okay, here's a graph of the values that we have. 1 unit, 0.83, 0.71, 0.63 down to 0.5. This graph isn't really to scale. The 0.5 is a little bit low compared to the 1, but let's not worry about that. And when we make a lower estimate, what we do is we take our average altitude, and for the altitude we take the minimum altitude, which on this graph will be the right-hand altitude, the 0.83 in the first interval, the 0.71 in the second, indicated by the red segments. We take our minimum altitude multiplied by the time interval. So that in this case we have 0.83 meters per second times per minute times 0.2 minutes. On the second interval, 0.71 meters per minute times the 0.2 minutes, and so forth, and we get lower estimates. Now, looking at our lower estimates for velocities are, as we've seen, 0.83, 0.71, 0.63, the lower value of the velocity on the trapezoid. And our delta s's are, of course, then obtained by multiplying each velocity by 0.2, and we get our delta s's. And we note that if we total our delta s's here, for the lower estimate, we get 0.64. We could also have used upper estimates using the 1 for the first interval, the 0.83 for the second, the 0.71 for the third, and the 0.56 for the last. Making lower estimates, upper estimates, and the upper estimates correspond to the green top to the rectangles. We obtain v equals 1, 0.83, 0.71, 0.56. So we have these delta s's. We note that this delta s, the second, third, and fourth, and fifth delta s's are all repeated here, so that if we take the difference between the upper and the lower, all these numbers will cancel out. We'll be left only with the 0.2 here and subtracting the 0.1 here. Those are the only terms that don't cancel out. And the difference there is, of course, 0.1. We get a total delta S of 0.74 for the upper estimate.